Thanks for attending my talk. So I'll be talking about chaos engineering, right? How you can build immunity in the production systems using chaos engineering. Actually, Gregor kind of talked about chaos engineering a little bit in his keynote today morning. So I'll just expand it more into what chaos engineering is, why do we need it, tools and practices we need to adopt. So let's actually get started. So I'll start by the definition of chaos engineering. Right? What is chaos engineering? So there's a wonderful website, principlesofchaos.org, and this is the textbook definition of chaos engineering. And you see a tool called Chaos Monkey. That's actually a tool. Netflix originated with chaos engineering, and they have this tool called Chaos Monkey. So in a lot of books you find this referenced. But what chaos engineering essentially is that it's a live experimentation on your distributed system, right? And the goal of that experiment is basically to A, learn and understand what are the distributed system failure points and how to sort of give you a guideline on the areas that you can improve upon. That's what chaos engineering is all about. And a common example of chaos engineering, I love this example that, when you're a kid, they give you vaccination. And what they're doing is they're actually infecting you with the virus or bacteria or whatever it is, right? And the goal is not as much as to infect you, but let your body develop the resistance. So actually you have some disease like that, you can recover from it. So chaos engineering is kind of the same thing. It's actually injecting failures in your system to build resiliency. But before I actually expand on what chaos engineering is, I want to start with why we actually need it. So, any textbook problem, they teach you about all sorts of testing, unit, integration, security, etc., etc. And typically how it happens is that when you build your system and you put it in production, you've tested your components individually together, how exhaustively, right, in multiple ways. So the question then is, why do we need another form of testing? Well, with all these testings, the focus of your test is actually on your actual system, right, how it behaves. But there is one thing missing in all of these tests, which is what chaos engineering actually does. And that one thing is, how does system behave when it's actually running in an environment? So unit testing, even integration testing, their focus is on the code, not on the interaction between the code and the environment. So there are some nice examples, right? You see the traffic light and you test it thoroughly and everything works. And it's deployed in the production environment and see what happens, right? It's basically useless. Same thing can be said about that cupboard drawer. So what is important in actual systems, distributed systems, is that you need to test the system itself and you need to test the environment on which that system operates. And that's super critical. And that's what chaos engineering mostly focuses on. So the problem is that the world is chaotic, right? I mean, we are operating at a large scale. You're deploying your applications in AWS, Google Cloud, Azure, whatever your cloud environment is. And things fail at scale, right? There are many moving parts of a distributed system, your disk storage, things can go wrong. There are a couple of examples here, right? Hard disk fails, network goes down, etc., etc. Point is, the world is naturally chaotic. So you have to, there's no way you can actually prevent that chaos from not happening. But what you can do is to be prepared for it and know what to do when it actually happens. And that's what we're going to see how. So people tend to ignore the environment, right? I know we deploy the application in AWS. It's AWS job to take care of all the environment works perfectly. Well, it is, but the problem is there are things that are beyond their control. Things happen. And you can't just ignore the environment, right? So when you test it, even if you have a staging environment, which is exactly a replica of production environment, there are differences. And you have to take into account. So there's a common example of Mars rover, right? You're putting this probe on Mars. So you make an assumption of this is how my environment is going to look like. And you test, like astronauts test for zero gravity on Earth, etc. You kind of simulate the environment on your local testing environment. But the problem is you have made a certain assumptions about the environment. This is how the environment are. how do you know that those assumptions are correct? I mean, you're making an assumption that fine, the network is reliable. Is it? What happens if there's a network failure? The problem with the environment is beyond your control. Once your application is, let's say, on AWS or whatever cloud, that's it. You can't control AWS, right? You can control your application, but you can't control your environment. So environment is something that you should not ignore. So there are common fallacies of distributed computing, right? We tend to make an assumption that we have a reliable network, bandwidth, etc., etc. If you go to this website, they list you like 8 fallacies of distributed computing. But the whole common point is that never make an assumption that your environment works perfectly. It doesn't, right? What you need to do is you need to take into factor what to do if things fail. So understand how your environment, how your system would behave in case of a failure. Build resiliency in the system itself. So one of the common failure conditions is cascading failure. So a distributed system, there are these set of interconnected components, right? So one component depends on another component, that depends on another component. You test all these components individually, fine. But what if there's a component on the back end that fails and you don't see the effect immediately, but there's another component depending on it, which depends on another component, and eventually the failures kind of creep in. And what happens with these cascading failures is because there are so many moving parts of it, it's not possible for you to anticipate every kind of failure up in advance. And they're triggered usually by very unusual set of circumstances, right? Something that you never thought, and you have a problem with your system, and your system is running in production safely, everything's great for 1 year, you think everything is good. There is some very, very, very unique condition that gets triggered, and one thing leads to another, and ultimately you have a crash. Turns out this actually happened. And this happened on February 28, 2017 in AWS outage. So this is actually the incident report. This report was finally prepared by the CTO of Amazon, Werner Vogels. So a lot of websites in US actually on the eastern coast stopped working because of this outage. And what happened was a simple storage service, S3 service, went down on the US East region. And there are a lot of other services that are dependent on it. So slowly and slowly everything started shutting down, and I think the outage lasted for 4 hours. And how it started, as per the report, was that one of the operators, he entered some wrong set of commands. And there were like hundreds of thousands of websites affected. This is a perfect example of cascading failure, right? You may not be dependent on S3, but there are other services that you're dependent on who in turn depend on S3. So even if S3 fails and you're not dependent on S3, your service is going to be affected. So point being, no matter who your cloud vendor is, no matter what your environment is, don't make an assumption that it would work fine. It just won't. So finally, let's get back to chaos engineering. What chaos engineering is it tests the interaction of your system in your environment. So typically in the stage, you have the developer local machine, you do some unit testing, then you have multiple environments, one or more staging environments. But the focus of that testing is testing your actual build artifact. But once you deploy it to the code, there's a new set of tests that actually have to be done in your actual production environment. You could also do it in pre-production or staging environment, and many people do it. But it has to be done on that actual production environment that actually tests, and the focus of those kinds of tests are actually not as much as your build artifact, but the interactions you have with an environment. So that's what chaos engineering is. Chaos engineering is the controlled experiments that you do on your distributed system. What these controlled experiments are is they are basically injecting failure, some kind of failure, some kind of condition that could potentially happen. An example that I'm running a service and there's resiliency built in, I have multiple instances of VM. What happens if one VM goes down? In an ideal world, you have a job scheduler, right? You have a job scheduler that should detect that this instance goes down. It should shut down that instance, divert the traffic to other instances, come up with a new instance, and ultimately divert the traffic back. How do you know if it happens? So what you do is you inject a failure in the system. You say, okay, let me actually screw up one of my instances. Let me actually shut down the instance, and I see what happens. That's an example of a controlled experiment, right? It's an experiment that you're doing that replicates what could potentially go wrong in your environment, or in this case, in your cloud environment or cloud vendor. So how's chaos engineering different from other forms of testing? We already kind of a little bit talked about it, but in all this testing, you are actually testing one particular known set of conditions, right? So you're doing a unit test on one particular component. You think this component can go actually wrong in ABC manner, and you test those ABC manner, right? Your unit tests are essentially a set of assertions that you make, right? Did it happen? Did it happen? If it didn't, I failed. Chaos engineering is a little more than that, because in distributed systems you have many moving parts, and you have many, millions and millions of combinations of things that can go wrong. It's not actually possible for you to enumerate all of them. So what chaos engineering is more of a learning exercise. What if this happens? What do I do? How would my system behave? So it's a process of generating new information, not testing for something that is already known. It's more exploratory, right? You test the effects of various conditions, and then you kind of generate more information, and often this information is a little bit subjective. It's not a objective yes or a no, pass or fail. It's like, well, the hard disk went down, or this network failure, my system did recover, but it took me 5 minutes to recover. So it's not a yes or a no, it happened, but it happened after 5 minutes. That's unacceptable to me. I want the recovery to happen in 30 seconds. Now, that's an example of subjective information. It's no longer a yes or a no thing. So one of the common misconception is like chaos engineering is about causing chaos. Well, that's not the end goal. Chaos engineering is not about causing problems, it's actually revealing problems, right? You already have problems in your system. Everybody has it. There's no such thing as a perfect system. What chaos engineering is doing is revealing them. And if availability matters in your system, well, you should be testing for it. So often the name chaos engineering actually, sounds a little bit counterintuitive, or if you go to an executive say, well, we're going to test your system by blowing up a couple of instances in production. How does that sound? I'm not sure if CTO would really buy it, right? So how chaos engineering actually started was Netflix actually came up with chaos engineering. And around 2008, Netflix started, and in 2009, they decided to go all in on AWS. They wanted to move to the cloud. And I think the person in charge, Adrian Cockcroft, he's actually a very famous guy. He speaks in a lot of conferences. And he's now actually at Amazon. He's the VP of Cloud Architecture. So he started that. And with that transition, what kind of happened was the environment that was up until that point was in your control, now is no longer in your control, because now you're relying on AWS for that. And I think around Christmas or something, there's an actual outage that happened, and Netflix was like kind of down for 24 hours or something at the peak season, and that actually caused a lot of revenue. So the whole chaos engineering concept was actually born from that point of view, that these things are likely to happen, and we can't control it. We might be able to, build resiliency that we would be able to recover if such a thing happens. So they generated a set of tools. It started with what is called Chaos Monkey, the stuff that you saw on slide number 1, right? That's Chaos Monkey. And Chaos Monkey was the most simple form of tool. So Chaos Monkey would just start with, shutting down certain instances of a service, and gradually they came up with a new set of tools, and they named Chaos Kong. Chaos Kong gained notoriety for shutting down the entire region. And finally, they have something called Chaos Automation Platform. And what Chaos Automation Platform does is that it actually periodically does live experiments on your running system, 24/7. So they have a whole team. One of my colleagues, actually, she works there. They have a whole team. They monitor. They do it. Everybody knows. And it forces the developer mindset that such a thing would happen. Don't make an assumption that it won't, and build a resiliency in your system right from the development stage. So it's an organizational shift, or like a change of mentality of how you actually develop your software. Your development cycle itself has to incorporate the fact that failures are going to happen, you have to take into account that and build resiliency right from the start. So they actually, all these tools, Kiosk Monkey, Kiosk Kong, later on got open source, and they have now what is called as a Simian Army. We'll cover that, which is basically a set of all of these monkeys and animals that are going to cause all sorts of disruption. They're open source, so you actually can access them. There's a book on it also. So before we actually start chaos engineering, let's actually talk about what are the prerequisites for chaos engineering. Well, as I said, chaos engineering is about generating new information, right? Chaos engineering is not about fixing known issues. So the first thing is, if you have a known issue in your system, then it doesn't make something like chaos engineering to work, because you already know there's a problem. Why would you do chaos? It's not going to generate any new information. The only information that you have is known. So the first thing about chaos engineering, before you start to adopt chaos engineering, is you at least fix all the known issues of your system, right? That's the first prerequisite. The second thing is that you're going to inject a failure, and then you're going to observe what's going to happen. How would you observe it? Well, you observe it because you should have monitoring, right? So the second prereq is that you should have adequate monitoring on your system. And I'm emphasizing the word adequate because, monitoring again is a little bit of a gray area in the sense what kind of monitoring you have. And some monitoring might just, monitor the instance of health, of services, and so on. But you need like detailed monitoring. You need like logs. You need to know what's actually happening inside the system. So you need to have adequate monitoring for chaos engineering. So principles of chaos engineering. Like how do you incorporate? How does chaos engineering work? Well, your system is working in what is called as a steady state, right? You have certain hypotheses. I have a service. It takes a request, process it, write something to DB, whatever. And you're making, in a steady state ideal world, you're making some assumptions, right? My resources are all fine, my network, hard disk, everything works good. And then what you start is injecting these failures or very real world events. And these events are something that mirrors a distributed system failure mode. So what is a distributed system failure mode? Well, a distributed system failure mode is a possible configuration, a possible way in which your system can actually fail. So you vary. One example I pointed out was hard disk failure, right? So your service is, service has 10 VMs, you have 10 disks. What if one of them fails? So you sort of inject this failure, and you have to run this experiments in production. You could also run it in a pre-production staging, and usually most of the people would do, because if there is something wrong, it's better to catch it in pre-production and staging than actually it goes in production. That does not replace production testing, it only supplements it. So you have these experiments running in your environment, your actual environment, and then you kind of automate it. So that's what the chaos automation platform does, right? It's an automation, you need to run it. There are different ways of doing it 24/7. You need to have team monitoring, etc. And there's a concept in chaos engineering that says minimize blast radius. What minimize blast radius is start from small. Like don't inject a big failure like 2 of my 3 regions failed right from the start. Start small, because if you inject a failure and if you inject a big failure and things go out of control, you may not be able to recover it. You start with something very small, right? One instance of one service, probably a tier 3 service. It doesn't even have to be, it shouldn't even be tier 1 or tier 2 failed, right? So you've isolated a very small failure that probably does not impact the customer directly. And if everything works, good. If everything doesn't, you've identified a weak point, fix it. It's like an iteration, right? So now we know that on tier 3 services, one of the resources we are fine. Let's actually move to tier 2 now. So we do the same thing in tier 2, you inject a failure. So essentially, you start with a very small blast radius and you gradually increase it. And ultimately, your goal is that if a big failure happens, either the service should recover or at least fail gracefully. In Netflix, I think they have something like that when you actually log in, you see the recommendations of all the movies, right? And if the service that fails, your stuff would still work, except you just won't have the recommendation. So that's a graceful failure, right? It doesn't really affect or terribly affect your user experience, sure, you might not have recommendation at that point of time, but if you are watching or if you are looking to watch one particular movie, you can still do it. Nothing stops you from doing that. Okay, so we talked about experiments, right? I kind of briefly touched upon it, but there's actually a sequence of steps that you actually have to do. So you first start to pick an hypothesis. So let's have an example. My hypothesis is that I'm immune to disk failure. Then you pick the hypothesis. Let's actually pick a scope. Scope is kind of a minimizing blast radius kind of philosophy, right? So this particular failure affects the set of services. So that's my scope, right? I'm going to inject a failure. If this thing fails, what are the metrics I need to observe in order to see what's happening? So observe metrics could be like, I don't know, my response times, my thresholds, my throughputs which sort of decrease, some kind of metric that I'm using. So you identify certain metric, and then you do is you notify the organization, hey, I'm doing an experiment, right? So it shouldn't come to them as a surprise that what the hell happened. You obviously tell them ahead of time, and you actually run the experiment. So you run the experiment, you have the metrics, you collect that information, you analyze the information, and if things work as expected, good, you increase the scope, and this is the automation cycle that you have. And things don't, you have identified a failure, fix that, repeat that experiment, and continue. So this is the experimental cycle that, pick a metric, define what is normal, inject a failure, and observe the difference. So here, what you have is you have two groups. You have a control group and you have an experimentation group. Actually, kind of, in medicines and in all this fields, you kind of do it, right? You're testing a new drug. So you have a control group and you have an experimental group. Let's say if you're testing, I don't know if it's ethical to test in animals, but whatever. You have a control group and you have an experimental group, and you kind of observe the difference, right? So chaos engineering is kind of the same thing. The good thing is you're not harming any animal or human in that process. You might be destroying the system, but still better than harming anyone. And then, you observe if everything works fine, good, you increase the scope, you repeat it, and if things don't work, there's a discrepancy, analyze the result, you've identified a weakness, and fix it, and repeat the experiment. So that's the experimentation cycle. Chaos Monkey, we kind of talked about it repeatedly. There's a source code for Chaos Monkey, how they did it, actually included in the link, so you actually can see, and they have good documentation also on it. So Chaos Monkey is like the most basic form of testing. Pick an instance, switch it off, observe the effect, and then you observe if your job scheduler will recreate it or not. If not, then you have identified a weakness, and if yes, everything works fine, then at least you know that when the actual server restart happens, you don't have a problem. So different kind of experiments that I have. Like, I mean, obviously this is not an exhaustive list. These are some of the things that you could potentially be facing. And one of the things is, it's not always a binary yes or a no thing, right? Something failed, something passed. Sometimes it's just about latency. My network works, but it's slow, right? So I have Kafka, I have like whole sets of brokers, producers, consumers, one topic accidentally got deleted. So there's always a concept of partial failure. And again, it goes back to the statement I made that chaos engineering, the information you generate from it is a little bit of a subjective in nature. It's not always a yes or a no, but it's all about like, there are numbers involved, there's like gray area in between. So you have all sorts of experiments, let's say you function through an exception. Were you able to recover from it? Were you able to gracefully fail for it? Injecting latency, Kafka, time travel, whatever you could think of. Simian Army. So what Simian Army is it's actually a set of tools, Chaos Monkey, Chaos Kong, and a whole bunch of tools. And these tools, all they work together to essentially try to disrupt your system. And if you can survive this army, then you're happy because you know when the actual outage happens, you will be fine. There's again a link, GitHub link for Netflix, so you actually can check and see what What's Indian Army is all about. So adoption in an organization. Now this is actually a little bit of a challenging thing. And why it is challenging is because there is a mentality shift, right? You're actually doing something live with production that can impact the revenue. So it's hard for executives to buy it. When the idea first came in, I mean nobody was buying it until they actually faced the issue. That's what happened with Netflix during that Christmas break. So, and also adoption is a little bit complicated because in an organization we have 50 teams. Some people feel they're ready, some people feel they are not ready. So typically adoption is not a yes or a no again, but there are strategies around adoption, right? There are strategies around. Some team says, well, we are willing to participate, but we don't want you to do anything in production. We are fine with pre-production environment, and that's about it. Some people will say, well, we are not ready, sorry. And some people might say, oh, we are confident, everything's good. So typically how it happens is that there's actually a kind of a configuration that you have to create. When my team was working on chaos engineering at JET, what they had was they developed all these tools, Chaos Monkey, Chaos Kong, and so on. And then we had a set of configuration for each team. So they can configure what are the services that they can opt in and opt out, and we kind of monitor it in the sense that you shouldn't opt out everything, or you can opt out everything, but if you do it for long, then there's something wrong, right? You're not building for resiliency. So there's that configuration aspect of it. Some teams should be able to opt in and opt out, and then you need to automate these experiments, right? They shouldn't be like one-off. You could probably start with something like one-off experiment, but eventually, as you go into sophistication of it, you want to do an automation, and you have to be willing to experiment in production. Why? Because that's your real environment. We talked about you want to test your interactions in your actual environment. Even if you do it on pre-productions and you think that you're fine, you're making an assumption that pre-production is identical to production. In my opinion, no two environments are identical. You can get close, and if there's something wrong with pre-production, definitely you can identify that and fix it. So you don't have to go to production in that case, but you can't ultimately skip experimenting in the production environment. So they have a concept of game days, and game days is like a fire drill, right? So when you have a fire drill, your manager tells you, well, there's going to be a fire drill, and everybody vacates the office in the morning, 10 a.m. and there are emergency points. There are actually 2 emergency points here also, by the way, in case you didn't notice. And everybody's supposed to assemble. And what you're doing is you're actually simulating an actual outbreak of fire. So game days is basically a practice that companies adopt to actually kind of simulate it. What they have is they basically, in my company, they usually have teams competing with each other, right? Of whose service is more resilient, and usually you have a prize money for the team, or actually some dinner outing or something. But game days is basically a collaborative environment where everybody will work with each other to simulate variant, to understand their system, to build resiliency. And there are obviously controls that you have to build around it, right? You have to have a success criteria, you have to have an abort criteria if things go out of control. You obviously need to have some dashboards for monitoring some metrics and so on, and you need to really practice it. Okay, these are the failures that we are going to inject. This is going to be our rollback plan if things go wrong. These are the criteria, success criteria, and so on. And it usually involves everybody. So right from C-level down to the lowest engineers, it kind of involves the whole organization. It's a great kind of team building opportunity. Learn about the system, share knowledge. Chaos maturity model. So typically, a chaos maturity model basically measures what's your adoption of chaos engineering, or how sophisticated of chaos engineering practice you have in your organization. And there are 2 dimensions to it, right? There's a dimension of sophistication and there's a dimension of adoption. So I'm going to examine each one of them in details. So sophistication, right? Sophistication simply means that how advanced is your practice of chaos engineering. So typically, there are 4 stages here. There's elementary, simple, advanced, and then sophisticated. And in an elementary, you start very simple, right? Elementary stage, you don't really run on your productions. You might run on your local machines, on your at best on your pre-stage, and process is very manual. There's no automation involved in it, and you might have something very simple. So you might have like disk restarts, network failure, and so on. And once you feel that's confident, you move to relatively simple but better than elementary stage, and there you have more sophistication on it, right? You have like experiments that actually run on production like traffic. So what you could potentially do is you can not as much as a divert or like some probably divert or just take an actual production traffic load and then apply it on your system and see what happens. In simple also, results are somewhat manually aggregated and analyzed, but it's actually running on a production traffic. And then you have more expanded events. You kind of want to bring some kind of cascading system, cascading failures also into your system, right? Finally, going from simple, you have advanced. And in advanced, you would start having experiments that are going to run in each stage of your system. So you have it, you have like typically local dev environment, goes to your build pipeline. Build pipeline has one or more pre-staging environment. You'll have a unit testing, integration environments, whatever. So you start incorporating chaos pretty much in all of them, and most of it is automated, right? And experiments start having a dynamic scope. So experiments start having the loop of, I'll start with small blast radius, increase it gradually and gradually, and finally, that's the most advanced. And before that, you have a sophisticated also, which is also experiments kind of run in productions, but there might be some frameworks, etc., and you might have to do something manually, manual terminations, and so on. So the another dimension to chaos maturity model is adoption. How much is your organization adopting it, right? So you start with the shadows. In the shadows, they like to call it. So you have few systems covered, and then this is usually how chaos engineering would start. That some of the teams say, hey, we should do something about it. There's no organization-wide mandate, right? And they're kind of an early adopter. They might do some infrequent, and then you move into something like investment where at least the higher management buys in, okay, this is something we should be doing. And slowly you have some resources dedicated to it. You might have multiple teams and so on, gradually moving to something like an adoption, right? Where you now have a dedicated team. And this is where most of the sophisticated organizations would have. They actually have a dedicated team that actually works for chaos engineering. And then you have a more complicated incident response system that if something happens, the person on call is notified, and critical services are now starting to practice. And then you finally have like cultural expectation. You have like built-in. All critical services would be tested. Chaos is regular part of engineering development cycle. It's regular part of onboarding. Participation is like the default behavior. You should not opt out unless you have a very good reason to do so. So there are a lot of organizations that use it. Netflix obviously started it. A colleague of mine does it at Microsoft. My previous employer, which was Jet.com, acquired by Walmart, so they do it. And there's this whole bunch of companies that actually form it. Some of them, obviously, not everybody is at the same page. Some of it practices it relatively less adopted. Some of them are more adopted. But it's actually entering a kind of a mainstream discipline now. So there are plenty of resources. For basics, you would just start with the Wikipedia page. Then Principles of Chaos, which is like the official chaos engineering page. Then if you want to implement the tools, there's actually a chaos toolkit. So chaos toolkit basically will have chaos monkeys and all those tool sort of libraries that you can take to build your own tools. Chaos IQ is actually a consulting firm. It's run by a guy named Russ Miles, Russ Miles and Associates. He's also a very frequent speaker in many of the international conferences. And then there's this company called Gremlin, and Gremlin actually were the people in Netflix who originated with chaos engineering, and they decided to leave Netflix and sort of commercialize these ideas. So that's what Gremlin is. There's a book on it by O'Reilly about chaos engineering. So, ending towards the conclusion, environment is something that you cannot ignore, right? It needs your interactions to the environment that needs to be tested. and failure is something that's bound to happen. So rather than, you know, putting yourself blind or saying, failure can't happen, embrace it, know what happens, know how to deal with it. And for best resiliency, you need to continuously run these experiments in production. And what chaos engineering ultimately does is it builds confidence in your system, right? You know your system can withstand failures, you know when it can gracefully degrade where and when necessary. Thank you.